So today we're going to be looking at polar regions, and we're specifically going to be finding the area of polar regions. And I have an example for you from page 740 of the textbook. It's example 1. And essentially we're just going to be finding the area of one petal of the rose curve that is defined by r equals 3 cosine of 3 theta. Now before you really do any calculations, a really good idea is to either sketch or use your graphing calculator to graph the curve that you're finding an area of. And this is so helpful really because a lot of these polar regions are quite unique. They're either rose curves or cardioids, but they're not your usual graphs that we're kind of used to. They're quite different. And when you're finding the area of parts of these curves and they're a little bit unique and you might not necessarily always know what they look like, it's really good to sketch it out to see what it looks like, especially because you need to know the parts that you're finding an area of, and you also need to know, the boundaries of it, especially for finding the area, because it involves an integral with boundaries. So it's a really good idea, if you do not already, to somehow produce a graph of the curves so that you can use it to help you find the area. Now, the area of polar regions is given by the equation A equals 1/2 the integral from alpha to beta of r squared d theta. And we already know that r is 3 cosine of 3 theta, so if we square that, that's going to be 3 squared, which is 9, times cosine squared of 3 theta, d theta. Now, we want to find alpha and beta, and that's really the hardest part in this problem, is finding the boundaries. And that's, again, why you want to use a graph. So I have the graph right here from a graphing calculator. And the first thing that you should probably consider doing is finding out where this graph even starts, where it even starts. So the graph will start when theta equals 0. So if you just plug in 0 to the equation, 3 cosine of 3 times 0, so 3 cosine of 0. And we know that cosine of 0 is 1, so 3 times 1 is 3. So we know that when theta equals 0, the radius is going to be 3. So the graph will start when the radius is equal to 3 at a theta of 0. So that means that the graph starts right here, because this is the radius of 3 and this is the angle theta. So that's where our graph starts. And you see that there are already arrows showing the path of the curve, but you can always solve for it by plugging in points. And we really also want to make sure that we do have these arrows, or we at least know where the graph, what direction the graph is going in, because that will also be important for us later. So now we know that this graph starts here, it loops around here, loops around again, and it ends right where it started. And so we're going to find the area of one of these curves. And it doesn't really matter which one, but we're going to take the area of this yellow one because that's just the one that the book does. But you can take the area of this one or this one. It doesn't really matter. They're all the same. So now that we've chosen which curve we're going to take the area of, now we want to find the boundaries. We want to find alpha and beta. And if you look at this graph, you're going to find that the boundaries are always when the radius is equal to 0. At the origin, it's always going to be all our boundaries are always going to be at the origin, because you'll see that the tip of each petal is at the origin. So if you start here and you loop around here and you end back here, that will be one area. And that's basically what we're finding here. So if you look at this graph, since we know that it starts here and loops around here, we know that our first boundary point is going to be the first place where r equals 0, because r is 3 here and it's constantly decreasing, and then it gets to 0 here for the first time, and that's what we want our first boundary point to be. So our first boundary point is going to be the first place where r equals 0. And now again, you'll notice that the graph loops around here and around here as well, and it only gets to the boundary point that we need for our second one at the very end. And after that, it goes back to where it started. And what this means is that the boundary point that we want next is the last place where r equals 0, because it goes through 0 here, and then it ends back over here. It's the last place where r equals 0. So the second boundary point is going to be the last place where r equals 0. So now we kind of know generally where our boundary points are going to be. And since we know that r equals 0, really we can just plug this into our equation. So if we solve for theta, so 0 equals 3 cosine of 3 theta, and just solve for theta. So cosine of 3 theta equals 0, because you can just divide by 3 and it's still 0. And if you pretend that 3 theta is its own angle, cosine of an angle equals 0 when the angle is pi over 2, 3 pi over 2, really any odd multiple of pi over 2. You can keep going. So then to find theta itself, you have to divide everything by 3. So pi over 6, 3 pi over 6, which is going to be pi over 2, 5 pi over 6, next one will be 7 pi over 6. You can keep going to 2 pi, which I'll keep doing. So 9 pi over 6, which is 3 pi over 2, and then 11 pi over 6. And then we hit 2 pi. So we stop there because the range is from 0 to 2 pi. So we know our first boundary is the first place where r equals 0, and that is the first theta, pi over 6. And the second boundary is the last place where r equals 0, 11 pi over 6. Now, we have to be really careful here, especially since we're taking this pedal and it's a little bit unique because, again, pedal only finishes at the very end. It starts, but then it doesn't finish until the end. So you have to be careful. You can't make it from pi over 6 to 11 pi over 6, because if you do that, you're taking the area of this whole region, so this pedal as well, and this pedal, and this pedal. You're taking the area of all 3 pedals because you're looping around completely. But we know that the last boundary that we want is 11 pi over 6. We know that's what we want. So you can call 11 pi over 6 negative pi over 6. It's for the same reason that 0 is equal to 2 pi. It's because the domain is like all multiples of 2 pi. So 11 pi over 6 is equal to negative pi over 6. So if we go from negative pi over 6 to pi over 6 instead of pi over 6 to 11 pi over 6, we're only going to take the area of one pedal. Because if you think about it, negative pi over 6 is right here. Here, I'll take a different color. Negative pi over 6 is right here. And then pi over 6 is also right there. But from negative pi over 6 to pi over 6 is that path. And that's the path that we want. And keep in mind that, again, if we took pi over 6 to 11 pi over 6, it would be this path. Oh, sorry. It would be, okay, that's messed up, but it would be this path, basically. And again, look at it, make sure you notice that it's taking into account, all 3 pedals, and we don't want all 3 pedals, we only want 1 pedal. So that's why it's important to keep in mind. You have to be careful of your boundaries. So we want it from negative pi over 6 to pi over 6 and not pi over 6 to 11 pi over 6. So make sure you see what you're actually taking the area of. So now that we know our boundary is alpha will be negative pi over 6 and beta will be pi over 6, we can finish our integral. So we can take the 9 out. Yeah, we took the 9 out, so it's just going to be cosine squared of d theta, cosine squared of 3 theta, d theta. And then you can just integrate. So cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. But since theta is equal to 3 theta, 2 times 3 theta is 6 theta, so it's going to be cosine of 6 theta over 2 d theta, from negative pi over 6 to pi over 6. And then you can just integrate as normal. So this is going to be theta over 2. And this is going to be sine 6 pi theta, because you take the opposite. So the derivative of sine of 6 theta is cosine of 6 theta times 6. And we have to account for the 6 in here. So we're going to divide by 6, because when we take the derivative, we multiply by 6. So sine of 6 theta over 12. And this is from negative pi over 6 to pi over 6. And then when you solve it out, you get 9/4. I just took out a half really quickly. Pi over 6 plus pi over 6. And this occurs, I kind of just simplified it really quickly, but sine of 6 times pi over 6 is sine of pi, which is going to be 0. And the same thing for negative pi over 6. Sine of negative pi is also 0, so this is all going to be 0. So basically we have pi over 6, because remember I took out a half, so this is technically theta. So we have pi over 6 minus a negative pi over 6, which gives you pi over 6 plus pi over 6 times 9/4. And this ends up being pi over 6 plus pi over 6 is pi over 3. And 9/4 times pi over 3 is 3 pi over 4. And there we have the area of one of these petals, this yellow petal, of this rose curve.